Good morning. Today we're going to continue talking about continuity. We're going to finish up the note page that we did on, I guess that was Monday. All right. Before we do that, the homework you guys had was to try 1A, B, C, and D, and then 2A and C. So I just want to go over those real quick, kind of like bring us back to what we talked about earlier in the week. All right. So remember, when we were discussing continuity to figure out if it is continuous at a certain x value, there's three things we got to check. All right, we got to check if the limit exists. We then have to check to see if there is a y value, right? Or like an f of x, right? At that certain point, basically means we're looking for where the y value of the solid point is. And then if there is each of those things, is whatever you got in one equal to whatever you got in two? If all three of those things are true, then we have it's continuous at that x value. All right. So if we look at what is happening at x equals 1. At 1, from the left, we look at the limit first. The left, it goes to 1. The right goes to 1. So the limit exists. So then we go to where's the y value or the solid point. Look at the solid point of 1. It's right here. What is that y value? It is also 1. So since the limit is 1 and the y value is 1, that obviously 1 is equal to 1. That means this is continuous. Now, the important thing is how you're going to write this. So you'd write continuous, and you just have to put CONT, because you could just put B/C. The limit of f of x, so you always put the limit of f of x, as x approaches, now the x value you put in depends on which prime you're doing, in this case it's 1, equals f of 1, because the limit is equal to the y value. That is why it's continuous. So there's the first one, A. All right, -3. -3. This is -3, right? So we do the limit. From the left, it's going to 2. From the right, it's going to 2. So the limit exists. So we move on to step 2, which is what is the y value, which means we find the solid point. There's an open circle here, but I care about the solid point. All right, the solid point's at 0. So the limit was 2. The y value is 0. They are not equal to each other, right? So we just care that there is a y value, and there was. But here, this doesn't work. 1 is not equal to 2, right? Step 1 is not equal to step 2. All right, the y value was 0. The limit was 2. So when that happens, we say not continuous, because the limit of f of x as x approaches, in this case, -3, does not equal f of -3. All right. So it looks just like the first one. It's just that we got to step 3. They weren't equal. When they're equal, they are continuous, and you write that way. When they're not equal, you write this. All right. X equals 0. So if we look at 0, from the left side, I'm going to -1. From the right side, it's 0. So the limit does not exist. So there is no limit. So you don't have to do anything else, and you just write not continuous. Because, and so when the limit doesn't exist, you write because the limit as x approaches, in this case it's 0 of f of x, does not exist. D and E. All right, so anytime there's no limit, that's what you write. All right, last one. As x approaches 3. All right, at x equals 3, sorry. So there's an asymptote. So don't waste any time checking for a limit on an asymptote. We cannot have a point on an asymptote, which automatically means that this step is going to fail. 1, it might have a limit, might not, who cares? Just go right to 2 and just write that whenever you're in an asymptote, it is not continuous because f of whatever, in this case is 3, does not exist. And there you go. All right, so we have 4 examples. 1 where it was continuous, that's how you write it. B where step 3 failed, so that's how you write it. C where it's step 1 failing, this is how you write it. And the last one, D, with 2 failing, and that's how you write it. All right. All right, so then you had to do 2A and C. All right, so you have A and C here. All right, now remember, the 3 types of discontinuities we have are finite, infinite, removable. Infinite and removable have to do with fractions, all right? And that's where the bottom is equal to 0, all right? So whenever you see a fraction, we have to worry about infinite and removable. So what we want to do is we want to, if you can factor it so that it's easier to see what makes it equal to 0. This factors to x plus 3 and x minus 1. Now, don't cancel anything out yet, all right? Find out what makes that equal to 0. That is negative 3. So you write x equals negative 3. What makes this one equal to 0? It's 1. So negative 3 and 1 make the bottom equal to 0. So that's where we're going to have discontinuities. Now, if anything cancels out, which it does, x minus 1 cancels out, I'm removing it from the problem. So 1 came from x minus 1. So since I removed it, that is a removable discontinuity, right? That is removable. Okay. X plus 3 is not canceled out. So negative 3 does not. That when it doesn't cancel out, that is called an infinite discontinuity. All right. Now, finite has to do with multi-rule. It also has to do with rational absolute value, which we're going to end up not doing at all with problems like this. So when it comes to finite, it's just going to be piecewise. Now, but what you do have to be aware of is when you have a piecewise, in each thing here, notice that we have a fraction here. What makes the bottom equal to 0 there? 2. And 2 is less than 3, so I have to worry about it. And x minus 2 doesn't cancel out with anything, so it's not removable, it's infinite. So we have x minus 2 infinite. Sorry, x equals 2 infinite, sorry. All right, then to check the finite, you plug 3 into both x's for all the x's. If you get the same thing, then it's going to be continuous, so that means it's not going to be any discontinuities. But if they're different, then it's going to be a discontinuity, not continuous, and it means it's finite. All right, so let's see. So I plug in 3. 4 times 3 is 12. 12 plus 3 is 15. 15 over 1 is 15. 3 cubed is 27. Minus 3 is 24. They are different, which means I do have a discontinuity happening at 3, and it is finite. All right, so that was just a quick review of what we did earlier this week and the homework problems I told you to look at. All right, so now we're going to go and look and finish the rest of the notes. All right, so this was our note sheet. This is where we left off. All right, we just have to do this bottom part of the second page. All right, and so for these two types of problems, so there's a typo on this. So we're going to do 5, and this is supposed to be negative 2, and this is supposed to be 1. All right, otherwise you won't be able to do the problem. All right, so what we're trying to do is we have two multi-rule function, piecewise function. We have 5 when x is less than or negative 2. We have ax plus 1 when x is greater than negative 2. We want to find the value for a so that this function is continuous for all reals, which means there's no jumps. So what needs to happen is when I plug in negative 2 into both equations, I need to get the same y value. Well, I got to figure out what a has to be in order for that to be true. So what I'm going to do is I'm going to plug negative 2 into there. There's no x to plug into, which means it's just 5. Equals, I plug negative 2 into this x and get negative 2a plus 1. And I set them equal to each other. And then I just solve for a. So 4 equals negative 2a. A equals negative 2. So a has to be equal to negative 2. If a was negative 2 and I had negative 2x plus 1, when I plug negative 2 into both, I would get 5, and that means I would have a continuous function. So you just plug in whatever this value is into both equations and set those two values or expressions equal to each other. All right. So for B, a little bit different because we now have 3 equations. All right. So what I want to do is let's forget about the 3 and this 3 here. Just worry about the negative 1. And let's treat it like we just did before. The difference in this one, there's 2 variables we got to find, A and B. But let's start it the same way. We're going to plug negative 1 in for this one. There's no x, so it's just 2 equals. And I plug negative 1 in for that x. Negative 1 squared is 1. So I get 2 is equal to a plus b. All right. Now that I did that, let's now do the same thing for the 3's. So now we're not worrying about the top equation or the negative 1. Now we do the same thing with 3. Plug 3 into that equation. 3 squared is 9. So I would get 9a plus b. and then I plug 3 into this, and I get 4. All right, so I get 2 is equal to a plus b, and I get 4 is equal to 9a plus b. All right. So the thing that's different here, I now have a systems of equations. I got to solve for a and b. So what I would do is I would figure out that I need to multiply this top equation by a negative. Make this -2 equals negative a minus b. 4 equals 9a plus b. The b's cancel. I'm left with 2 equals 8a. So a equals 1/4. All right, or 1/4. All right, so a equals 1/4. Then to solve for b, if I plugged a into here, 1/4 plus what equals 2? Well, it'll be 1 3/4 or 7/4. So I just plugged in a to solve for b. So I would have to have a would have to be, all right, in this problem, if a was 1/4 and b was 7/4, if I plugged them in for a and b, it would be so that this would be continuous. And the reason it'd be continuous, because if I were to plug all these points in and graph it, they would all at -1 and 3 have the same y value, and there would be no jumps, nothing like that. That wouldn't happen. All right, they would all, the graphs, be going from the same points. All right, and like I said, we'll do more practice with these. So that's how you do those types. All right, last thing is it says use the IVT. All right, that stands for the intermediate, and I'm not really quite sure how to spell intermediate. I think that looks good. It stands for the intermediate value theorem. Okay, and it's listed right here. If f is a continuous function on an interval from a to b, and k is any number between f of a and f of b, then there is at least one c in the interval a to b such that f of c equals k. All right, what does that mean? Okay, it means this. If I call this point A and point B, all right, if we have 2 points and we have a continuous function, meaning that there's no asymptotes, jumps, whatever. So once you pick up your marker, you can't, all right, you can't pick it up again, all right? Once you start drawing it, tracing it, you can't pick it up, so you have to go from A to B. If there's some y value between A and B, so somewhere between here and here, that, and just say it was like right here, there has to be an x value between A and B where the graph is going to cross that spot. All right, so as long as there's a y value between A and B, there has to be some x value that's going to have a y value of that. All right, that's what the intermediate means, like between, like intermediate school, sometimes called middle school. All right, elementary, high school, the middle school, sometimes called intermediate. All right, so it's in between. So we have an in between value. All right, that's basically what's happening. Now, the way we're going to, for this example, it says use the IVT to show that the polynomial function x cubed plus 2x minus 1 has a 0, which means that you get a value of y. The y value is 0, between 0 and 1. All right. So what we're going to do is these are the 3 steps that we do with intermediate value theorem. The first 2 we always do. The third step is only if it tells us we have to find the x value. In this problem, example 1, we don't need to actually find it. It just says use it to show that there is a 0. We don't actually have to find the 0. Okay. So the first step that we are always going to do is check if the function is continuous on the interval. Well, this function right here is not a fraction. It's not a piecewise. It's not a greatest integer. It's going to be, the only thing you really need to worry about is looking for a fraction. It's going to be continuous. So what you have to write is f of x is continuous on the interval. When I say the interval that you're given, in this case, it's 0 to 1. All right, so just say that it's continuous, meaning we know there's no holes, jumps, or asymptotes. All right, the second thing you were going to do is you're always going to plug in the beginning and end of the interval into your function. So in this case, it is 0 and 1. And we're going to get the y values for when we plug in 0 and 1. So here, when I plug in 0, I get -1. When I plug in 1, I get, what is that, 1 plus 2 minus 1, 3, it's 2. All right, so I get -1 and 2. So I'm checking to see if 0 is in between those two y values. It is, so we're good. So right there, that says, so basically what they're saying is, and you don't have to draw this part out and do the problem, all of this would be good. You'd be done. So at 0, -1 is your first point where you're starting. 1, 2 is where you're finishing. What it's saying is, since 0, y value 0, is in between -1 and 2, and this is a continuous function, there has to be some value, some x value between 0 and 1 that is equal to 0, that crosses the x-axis. Has to be at least 1. All right, and it makes sense. There's no way I can go from a to b if it's a continuous function without crossing the x-axis. All right, and that's what this is showing. Now, if I were going to find this, if I had to do step 3, you do not for this problem, I would just take this function, x cubed plus 2x minus 1, and set it equal to whatever this number was that we're checking is in between, which is 0, and solve. Obviously, this one's a pain in the butt. I wouldn't give you something like this to actually solve, hence why I didn't do it here. All right. So now, last one on here. Use the IVT to show that this function has a c value on this interval such that f of c equals 6. So instead of checking if 0 is in between, we're now checking if 6 is in between. All right. This is our A and B. This is our starting points. All right. These are the numbers that we're going to plug in to this. All right. The first thing you have to check is if it's continuous or not. Now, this is a fraction. Where is this not? So 1 makes the bottom equal to 0. So at 1, you would have an asymptote. However, notice 1 is not on my interval. That 5/2 is 2.5. So 1 is not between 2.5 and 4. Therefore, it's not a continuous for all reals, but I don't care. I just care that it's continuous on the interval. So I write f of x is continuous on the interval from 5/2 to 4. All right. Now, a little hint, pretty much every problem I give you on an assessment with IVT, the intermittent value theorem, will always be continuous on the interval because I'm not going to, if it wasn't continuous, you would have to solve the problem. And I'm not going to give one like that. Okay. So then the second thing you're doing is you're plugging in f of the beginning of the interval, which is 5/2. You're going to have to do some fractions here, and f of 4. All right. So do me a favor, go ahead, plug in 5/2, plug in 4 into f of x and see what you get. All right, so wrote on my work to save some time. All right, so what you should have got is 35/6 and 20/3. All right, this one, 5/2 could maybe give some trouble just because it's fractions. But 5/2 squared is 25/4, right? 5 times 5 is 25, 2 times 2 is 4. Plus 5/2. So 25/4 plus 5/2. 5/2 is the same thing as 10/4. So I do 25 plus 10, which is 35/4. 5/2 minus 1 is 3/2. So I get 35/4 divided by 3/2. When you divide fractions, the same thing as multiplying by the reciprocal. So I did 35/4 times 2/3. The 2 cancels, make it 1. With this 4, it'd be a 2. So 35 times 1 is 35. 2 times 3 is 6. 35/6 is a little bit less than 6, right? Because 36/6 would be 6. So it's a little bit less than 6. Plug in 4 is a little bit easier. You end up with 20/3, which is a little bit bigger than 6. Why does that matter? Because I'm checking to see if 6 is in between them, and it is. 6 is definitely in between them. So what that is saying is there is some value, x value, on this interval such that this function is equal to 6. Now, the difference with this problem is it says find that. So what you're going to do is we are going to set our function x squared plus x over x minus 1, set it equals 6. Now, I better get an answer that's between 2.5 and 4. There has to be. If you don't get one, that means you did something wrong because we show that there has to be one. All right, so if I multiply both sides by x minus 1, right, cancel that out, I get x squared plus x equals 6x minus 6. All right, set it equal to 0, x squared minus 5x plus 6. And I factor that, and I get x minus 3, x minus 2. So I have two possible answers. I have x minus 3, which is 3, x minus 2, which is 2. Go back and check the interval. Which one of those is not on the interval? If 2 is less than 2.5, it's not between 2.5 and 4. 3 is good. So the value is 3. All right. So just to recap, we first checked it with the function is continuous on the interval. All right. We then plug in the two endpoints and we check to see if the value that we're trying to check is in between those two y values. If it is, then we go and set the function equal to that y value and solve and make sure our final answer is on the interval. All right. So that wraps up continuity. What I would like you to do is on that review sheet, which is actually right here, to do me a favor and just try 3 and 4. All right, try in 3 and 4, and we'll go over those in class tomorrow, and we'll review everything, all the continuity stuff. We're all done chapter 1. We will probably have a chapter 1 test, or I should say, it's some sort of assessment on Tuesday, the virtual day. All right. I hope you guys have a good day, and I will talk to you tomorrow.